Okay, so we're gonna start moving on to trig identities. This is chapter 5, it's our third unit. So this is the last part of, like, not say foundational trig, but the last trig unit that we're gonna cover before we move on to polar curves, which does involve trig. Sometime probably in late October, I'm guessing, is when we'll get to that. I haven't decided when this test will be. Actually, I do have this test date, but I haven't done the pacing yet. I think that's what I meant to say. As for your exam, I haven't graded them yet. I do have 2 free periods coming up, so I hope to grade them soon. They look pretty good on the surface, so we'll see how they look. And I hope to have them updated for interim grades later tonight. They're due by midnight, interim grades, so I hope to have that done. I was taking care of my Algebra 2s last night, this morning. Obviously, I was really tired yesterday for obvious reasons. So I'll try to take care of it. I do want to go over the test still. So if we have some time near the end, I'll at least go over parts of the test. I do have the test here. I still need to upload it. So if we don't, then we could always push it out till tomorrow. We could go over tomorrow as well. Anyway, identities. So you guys did cover this in Mr. Band's class, and I actually did chat with him last week before I left for Chicago, and he said you guys did cover a good amount of identities. So this should be review. Now an identity, even though you see an equal sign, it's a little different than an equation. So really quickly, like this right here is an identity because isn't the left side identical to the right side? If I distribute, wouldn't they be 100% the same? So if I tried solving this, what would happen? Everything would cancel out, right? Or you get 0 equals 0 if you cancel out negative 6s. What do you say when that happens? True for all real numbers, or infinitely many solutions. That works too, exactly. So it's not really an equation because you're not really finding a particular number that makes it true. Everything makes it true. That's what's called an identity. The left side is identical to the right side and vice versa. If I had 2x minus 6 equals 10, now that's an equation that I solve because it has one answer, right? And graphically speaking, you have a line, 2 lines actually, and they touch somewhere. In this case, I think it touched at 8. So that's an equation. So it's not confusing because now we're dealing with identities, not equations. But obviously in the realm of trig, so you guys have seen some of these things already, right? Like tangent sine over cosine, cosecant is 1 over sine theta. Those are trigonometric identities. It's true for any angle that you pick. Now the basic ones, you guys should know these already. Cosecant, secant, cotangent are reciprocals of sine, cosine, tangent, respectively. And of course, you could reverse some signs of reciprocal cosecant, cosine reciprocal secant, tangent reciprocal cotangent. Tangent sine over cosine, that's like y over x on a unit circle, right? Y and x, or x and y for cotangent. We've talked about these already, so I don't think there should be anything brand new. We've actually kind of done these, right, in our last unit. So these all make sense, right? We're okay with these. And just what is an identity? It's when the left side is identical to the right side. Okay, so any value of x or theta would work or be true for the relationship. Some other questions to talk about. So theta equals 0 is in a domain of validity of exactly 3 of the basic identities. So it's kind of a weird question, but if I plug in theta equals 0, so some of these won't work. Some of these will be bad. Which one of these would be bad? Or actually, which ones would work? Let's put it that way. Which ones would be valid for this to be my domain? Yes. What else? There's 2 more. Yep. And what else? Yep. All 3 of those. That's because cosine theta equals 1 and secant theta also equals 1. The problem is that this equals 0. That would be 0. Well, that would be undefined. So forget about that one. That's also 0. So yeah, that would cause problems, right? So just keep that in mind, that there's some restrictions for these identities. So which 3? Again, secant theta, cosine theta, and tangent theta, so I meant to say. For exactly two of the basic identities, one side of the equation is defined at theta equals 0, and the other side is not. That was for sine theta. Um, and also, wait. Yeah, you're right. You're right. Yeah, cotangent, right. My apologies. And then for exactly three of them, both are undefined. And that would be secant theta. That would be cosecant theta. And that would be actually, wait one sec. Um, shoot. Okay, what is going on here? That's not gonna work. Okay, much better. Sorry, my bad. That was supposed to be for that one down below, and that was supposed to be um uh which one was that gonna be? That was a cosecant. Wait. Wait, it works. Let me go back. Now I'm confusing myself. It was, yeah, secant was fine. Cosine was fine. Tangent was fine. Um, cotan, secant, cosecant. Oh, you're right. The cotan. You're right. Wait, is that right? Because undefined. Oh, shoot. Hold on. I made a mistake. My apologies. That one's fine. That was supposed to be, hold on. Cosine's fine. Secant's fine. Sine's fine. Now I'm just like totally confused myself. Secant, cosine. Tangent theta was fine. Um, yeah, that was also not fine as well. Because you get undefined both. Oh, is the tangent theta? No, that's fine too. Oh, one over cotan. You're right. My apologies. You're correct. Yeah. Okay, now I got it. That's why I should have wrote these out more explicitly. My apologies. I should have done this. Secant theta is more of cos theta. Cos theta. And that one was tan theta was sine theta cos theta. Okay, those three are cool with a equals 0. These two, it's fine on the left side, but not fine on the right side. And these three were not fine both left and right sides. Okay, my apologies. Okay, I think we get it. I think I'm taking too long with this. Let's move on. You guys get, understand what's undefined. Let's move on to Pythagorean trig identities. That's an important one. So just Pythagorean theorem, right? If you look at the unit circle, the radius is 1. And remember, x is cosine and y is sine. So if we substitute cosine theta squared for x squared and sine theta squared for y squared. And remember the difference. Well, not the difference, but remember that's the same thing as saying that, right? And that's the same thing as saying that. Mathematicians are lazy, so we like to sometimes make things easier. So if we put a square next to the cosine in between the cosine and the theta, it's the same thing as parentheses cosine then squared, or parentheses sine, then squared. So of course we get the following: cosine squared theta plus sine squared theta equals 1. This is a trig identity that even my friends who are in my mid-40s, they still remember this, who don't do anything with math, like they're in sales or legal or medical or some other profession or tech, but they don't use this stuff, but they still remember this. This is actually one of these identities who still kind of sticks with you. So it makes a lot of sense. It ties close to unit circle. We spent a lot of time with it. Now, there are two other variations of it. The two other variations, how would I get those? What would you... Do you guys remember the other variations that involve like tangent and cotangent and secant and cosecant? Yeah, totally. I kind of forget these sometimes. What if I divide everything by cosine squared theta? So it's fair treatment doing everything, right? If I do that, what would I get? 1 plus tan squared theta equals what? Perfect. Good. Or what if I decided to divide each expression by sine squared theta? Then what would I get in this case? Yep. Yeah, and if you have a hard time remembering them, just do the derivation. It's not that hard. It's pretty simple. But you might see some even wackier variations of these where the one moves to the other side, or you make one of them negative. So I think at its core, the foundation, no x squared plus y squared equals 1. That's from the unit circle. That's equation circle, by the way, and it uses Pythagorean theorem. And the fact that we know that x is cosine because that's adjacent over hypotenuse, x over 1. Sine is y, that's opposite over hypotenuse, y over 1. If you do the substitution, the Pythagorean trig identity makes a lot of sense. And then just doing variations, dividing both sides by sine squared, cosine squared, we can get other parts of it too. So all right there. So now let's talk about simplifying because the homework will involve quite a bit of that. That one should be pretty straightforward, right? What's the final answer here? Yeah, easy peasy, right? Okay, now we get to some fun stuff. So I like this stuff because this is where things get a little crazy. They get a little more interesting. You have to think a little more critically. So how's I able to do that so quickly? What did I kind of do in my head? Yeah, these are already add to 1. So you can rearrange if you want to. If you want to show the rearrangement of addition. So remember addition is multiplication or commutative. You can reverse them. Like 2 plus 3, 3 plus 2, 2 times 3, 3 times 2. Same thing, right? So you totally have that luxury of doing that. No, don't do it with minuses or division, obviously. You can't just reverse minus and division. But if you have addition, yeah, just bring them closer together. It's 1. But we're not out of the woods yet. Because don't we have another identity for 1 plus tan squared? What's the identity for 1 plus tan squared? Yeah, exactly. And if that's not painfully obvious, usually write them down first. Like write down sine squared x plus cosine squared x equals 1. Do the other two variations, and then that will kind of just appear like, oh yeah, that's what I do. And then that will just be secant x. So that's the whole point of simplifying, right? These problems are run with an intention that we want things to whittle their way down to a really nice, simple expression, like one expression or maybe a couple expressions. Like right now, I have like 4 different things, a fraction, a bunch of addition, right? If we are careful with how we substitute, we could totally get this down to a very nice, simple expression. This is advantageous because this class is called Precalculus for a reason. As we move on to calculus, when you start doing derivatives or integrals, all these wacky calculus things in a year from now, actually, we'll start doing some calculus less than a year from now in this class. You're going to have these expressions you have to deal with. You do have to be able to simplify it to make it easy to do calculus principles. That's why we're doing this, to spend the time, not to torture you guys, but to really make your life easier next year. So anyway, let's move on to the next one, cofunction identities. So I think we had this on quiz, if I'm not mistaken. You should know that cosine and sine are called cofunctions because co is a complement, right? So cosine is a complement of sine. So like, let's say angles A and B are complements, right? That means they add to 90. So angle A is 90 minus B, or if you replace with radians, angle A is pi over 2 minus angle B. So it says here, notice what happens when we use the usual triangle to find the 6, blah, blah, blah. So let's say we have this here, right? I'll call it C. C is the right angle. And so I call this little a, little b, and little c. And we'll focus on this angle right now, right? So what's sine of angle A? What's cosine of angle A? What's tangent of angle A? Okay. Now let's do cosecant, secant, and cotan. You get C over A, C over B, and of course B over A. So all makes sense? All right. Now I'm going to use the same triangle, but my focus is going to be on angle B now, right? Still label sides the same way. That did not change. So sine B, cosine B, tan B. What's sine of B? And what's cosine of B? And of course, B over A. And we reverse again. C over B, C over A, and A over B. Now, I'm going to get a little highlighter here. Notice how this is the same as this, right? That should make sense because what do A and B add up to? 90. So the sine of an angle will equal the cosine of its complement. As it should. This goes complement of sine. Those are the same ratios, right? You see that? Or well, let's use a different highlighter. Excuse me. Let's go purple. That the same as that, right? We see that. That totally makes sense. Because those are complements. Or let's get a different highlighter again. This is the same as this. So we see the three different co-function identities. I could do more highlighting, but you guys get the point now, right? A cosecant is going to be the complement of secant B. Yeah, right there. So those are also complements, but you guys get the idea that we have all these different co-functions, right? So here are the co-function identities. Sine of pi over 2 minus theta is that, and so forth. And you can reverse them as well. And we'll talk about some indifference formulas as well. Not today, but some indifference formulas you can apply the same principles. You plug in pi over 2 for one angle, theta for another angle, and kind of work it out. It's kind of a wacky formula, which actually I think I do give to you guys. I think that's the only one I do give. So I do give some. I'm not a total monster, but this one you guys know as well. I don't give this one. Okay. So let's keep moving. Questions though before I keep moving? No? All right. Even odd identities. We talk about odd even functions. So you guys should be comfortable with that by now. That really just comes back to the unit circle again. Everything kind of pun intended comes full circle. Get it? No? All right. Okay. Okay. So so say for example that's 30 degrees, right? And say I go down this way, negative 30 degrees. What's true about the x-coordinate at both those points? Are they the same? So the cosine will be the same. How about the y-coordinates? Are they opposite in sign? So sines will be opposite in sign. And then tangent is a tangent of the ratio of y over x. Well, y changes sign, but x did not. So tangent will also change sign. So if you just think of it like that, it's not that hard. Also, think graphically, right? Sine does this. Is that symmetric about the origin? If you rotate 180, do I get back to the same configuration? No, you do for sine.
Oh,
Yeah, but this cosine, is that symmetric about the y-axis? It is. So it has to be an even function. Tangent does this, right? If I take that and rotate 180, do I get back to the same configuration? So it's an odd function. So that's going to be odd, odd, and even. And expect the same thing for secant, cosecant, and cotan. They'll be the same way. So now let's do a couple of identities just to work it out. That one's just going to be just cosine theta because just copy what's above, right? That's pretty simple. And what's cosine theta according to this problem? So the answer is 0.34. Yeah. I'm here. This is a little tricky, but I'm going to do this. You guys see what I just did right now? What slight algebraic manipulation I did? What did I pull out? Which is fair because I put it back in, I'll get back to the sine thing. Now, if you sine of a negative angle, remember it's an odd function. So what can I do with that negative afterwards? You can pull it out. You're allowed to do that if it's an odd function. Yep. So it becomes this. So we're starting to become a little more fluid with our algebra as well as our understanding of identities. And sine pi over 2 minus theta is the same thing as cosine, right? So what does that equal? Negative 0.34. Not terribly obvious right from the beginning. You see a different function. You see a theta and minus pi over 2. But if you think about, I can pull negative out. Okay, that's just an algebra. And even though that's the transformation, it's an odd function, pull that out as well. Okay, and I know cosine. I know that cosine is another identity. Co-function. Okay, and that's negative 0.34. But trust me, these will get more complex. We're just scratching the surface. Just scratching the surface. Okay, questions? Nope. Okay, we'll keep moving. Okay, simplifying trig. All right, now this is the real fun. Oh yeah. I think I might hold off in the interest of time. Maybe I won't do example like part G. I might hold off on that for now. And then look at the homework. Can I see the homework pack?
9 and 10.
Okay, maybe not. No worries. Look at you. Right here. All right, love it. Maybe 9 and 10. Maybe. Let's see. Let's see. Okay. I mean, problems to help you with 9 and 10. That's what I meant to say. But for now, example 4, 5, 6, 7, 8. Let's do those for sure. So I'll guys kickstart with examples 4 and 5. Have you guys then do 6, 7, 8 in your table groups. I'll walk around and help you guys out. And if I could squeeze in some stuff from part G, I will. So you could do the entire homework. Because the homework, just is going to be this. Just handout. It says handout 11. I'm 13. I don't know why it says 13. Maybe that's from last year. I don't know. But it's just going to be the first 2 pages, page 1 and 2. Bless you. So homework should be pretty manageable. Anyway, let's do 4 and 5. Let's talk about it. Factoring is good. Foiling is good sometimes. Adding fractions might be good. You're gonna have to get awfully creative. And again, we're gonna step this up big time in the next couple days or 2 classes. So let's pull out sine x. Does that make sense? Common factor. And what's sine squared plus cosine squared again? 1. So final answer is just sine x straight up, right? Bless you. All right. Now 5, I probably should FOIL, right? First outside, inside, last. So if I do that, I should get secant squared x. And then I kind of know the middle term's going to cancel. How do I know the middle terms will cancel without actually doing it? Yeah, can you see the plus 1 minus 1? That's the difference of 2 squares, right? That's how we expect that to factor. So you want to be very adept with your factoring, right? Like, oh, if I had x squared minus a squared, I know it's x minus a, x plus a, or x squared minus y squared, x minus y, x plus y. So you kind of just recognize that. And I'm going to cheat. I'm going to go up and look at identities up here. But which one involves secant squared? Yeah, see how so it's a little variation of it. You move the 1 over. So that's the same thing as tangent squared x. same exact thing as tangent squared x. Now, I know you guys can be great at fractions because you guys are honor students, but I know fractions also was kind of covered a few years ago. And that's why I learned my conference. What you guys did a few years ago, I got a better understanding. What did fourth, fifth graders do, right? You guys do fractions. And what happened 4 or 5 years ago? Pandemic, right? So if you're having some little trouble with fractions, just talk to me. I'll help you out. Maybe we could do some extra practice. But remember, it's tan squared, sine squared over cosine squared. So you have a fraction up top, right? And down below, why don't you write that as a fraction as well? That's a fraction, right? And it can be a fraction, just put one below it. So you have one fraction up top, tan squared, sine squared, over cosine squared. Technically, you have another fraction down below, sine squared x over 1. What happens when you divide two fractions? Which one flips? The bottom one, right? So if you flip that, let me change colors for a bit of contrast. You should have sine squared x over cosine squared x times 1 over sine squared x. Now what happens to those sine squared x's? And then almost done. What's 1 over cosine again? That's squared, so it's secant squared x. So all that junk simplified really nicely to just one expression. Now, you could verify this when you're doing your homework. Tests might be a little tough, right? You don't allow a calculator, but you can verify this very nicely by just graphing this expression and graphing that expression. They should be identical. Or in Desmos, you can do the same thing. Desmos might be a better way to go. But you can always verify by graphing. Or you can plug in a number, plug in a random number for x, see what that is, what that is. I think graphing might be more efficient. But you can always verify by just graphing the beginning and end, and they should be identical. All right. Now you guys got you guys warmed up. Try 6, 7, 8 on your own. For 7, find the LCD. For 8, you're probably gonna want to do this. It's called the conjugate. And here, I would actually factor. So that's what I would that's what I'd recommend. So I'll freeze the screen, I'll work it out, then we'll discuss. And kind of decided I'm gonna hold off and going over the test until tomorrow with you guys. So tomorrow we'll go over the test, just so you know. And I should be able to pass it back to you tomorrow. And once we get done with this, Alex will have you guys get him do a survey and get set up on his app. Okay, I'm working it out, and I'll walk around and see how you guys are doing. All right.
Fine. You got them all? Well, you're all set. Yeah, just go okay with that one. Those my answers. Yeah, my questions so far. Wait, just look good. All right, sorry. Fine, fine. All right, yeah. Cool. All right, so those are my answers.
6 is kind of simple. That's the difference of 2 squares. So hopefully you guys got that pretty quickly. And the 1 plus tan x's as expressions cancel. We have tan x minus 1. For example, 8. So usually when you see something plus 1, the thinking you should do that expression minus 1, because then you're forced to issue a difference of 2 squares, which then allows you to use another identity, because secant squared x minus 1 is tan squared x. And do not distribute the tan squared x into secant x minus 1 in the numerator. Do not do that, because the whole intention is to cancel out the tan squared x, right? And the tan squared x's do cancel, leaving secant x minus 1. And that's a little simpler than what we had before. And then for 7, you usually want to bring fractions together. So you find the LCD. So you have 2 different denominators, 1 minus sin x, 1 plus sin x. They don't share any factors. So but they don't share any factors. That's okay. Put a little parentheses there. Now in this case, I will fold the bottom, so I can actually substitute for that expression, which is cosine squared x. Up top, when I combine the fractions, the numerators, the sin x cancel. I get 2 up top. You get 2 over cosine squared x, which is 2 secant squared x. So it's the same exact thing as those two being added. So all's good there. Okay, these notes going much faster than I thought. This is good. I got a little scared when I saw 6 pages. Oh my God. So I think we could do some equations. Before I do that, any questions at all? What's happening? So again, factor, conjugate, LCD. A lot of different things in your algebra toolkit, right? That you want to tap into. So we're just building upon things you guys have already done, right? All right. I think we can do some equations. I think I'm not gonna get to all of them. I think if I get to like maybe we'll do like up to 11. That might be good. And we could wrap up the other ones on Tuesday and keep moving part 2. Because I won't have any other airplane stories to tell you tomorrow, because I'm not going anywhere tonight. So anyway, example 9. All right. So now here, you want to get a very specific answer. So this is a restricted domain in a way. So not infinite possibilities. Remember the on the test, we had infinite possibilities, right? We had general solutions, right? Not the case here. This is more restricted. Before I get too carried away, we probably should move things around, right? Maybe let me try to think here. So maybe that could work, perhaps. Does that make sense so far? So what did I do on the left side? I split the fraction, right? And you're allowed to do that. There's no problem. Like, for example, what if I had like x cubed over y? Isn't that just x over y times x squared? Right? Wouldn't that be the same thing? Could bring it back together, make it x cubed over y. So there's no harm in doing that. But you have to get a little creative. Because think about what's cosine over sine. Okay, look. Okay, now we're on to something. Now, please don't do this. I will be incredibly unforgiving. Do this. Some students will do this. Why is that bad? What was that? But still, even if I do that, no, you could I could cross them off. Not errors necessarily. You wind up, here's what's gonna happen. You're not gonna get the full answer.
Oh.
You won't get the full story if you cross stuff off. You have to actually move that cotangent from the right to the left and factor it out, because that's going to be a solution we have to consider as well. So you cannot cross stuff off because you won't get all the possible answers if you do that. You might remember this. What if I like x times 4 equals let me think if this makes sense what I'm about to say. Um like some people cross these off, which is kind of bad. But here's the thing. Some people do this, they'll say 4 equals 1, and the answer is no solution. But really, what should I have done for this situation? I should move the x over, right? And then when you solve, what do you get? Yeah, actually, this works better with like squares. Let me take it back. What if I had this here? Okay, this is what I meant to do. Okay, I meant to do this. See, if some people will cross off these x's and say the answer is 4, which is true, but really, is that the full answer? No. Because what's the full answer? 4 and what else? X would equal 0 and 4, right? Sorry, I know you guys can't really read that. So you have to make sure you move all the terms to one side, because graphically speaking, there's more than one point of intersection for that purple equation I just wrote. So you have to do the same exact thing here. So let's put a cotan x to the left side. If there was a plus in the middle, obviously you can't cross them off. But I think that's what you guys are insinuating. But no, times you could, but still, we want the whole solution. So you got to do that instead. So see how that is a little more sophisticated, right? Cotan x times cosine squared x minus 1. So now I could actually solve it. Cotan x equals 0, or cosine squared x minus 1 equals 0. So cosine x has to equal what? Plus minus 1, right? At what x does that happen at? Where's cosine? Positive or negative 1? 0 and 0 and pi, correct. And we don't include 2 pi because it's not part of our domain. And where's cotangent going to be 0? Remember, cotangent is x or y in the unit circle. Where does that happen? And actually, just sorry. Yeah, power 2, 3 power 2s. Yeah, my bad. Sorry, I'm losing my mind. Yeah, it's 2 places. And you don't put the plus and pi business because we're not dealing with that, right? And then you could always go to Desmos. And do y equals parentheses cosine x raised to the 3rd power. Wait, why is it doing that? Hold on. That was weird. Don't know why I did that. Great. Hold on. Butterfingers here. Divided by sine x. And the other one's y equals cotangent x. Of course, they intersect a lot of different places, right? But if I focus on 0 to 2 pi, which is basically up to 6.28. See, I got those two answers right for sure. And hard to tell, but it should be at pi. Trust me, they do intersect there. So, no, not pi. I meant to say yeah, right. My apologies. Hold on. Undo. My bad. There we go. Yeah. Oh, but wait 1 sec. We do run into a problem. We do run into a problem. What problem do I run into? 0 and pi. That's gonna be undefined. Yeah, actually, I'm glad I graphed that because actually it wasn't hitting it, right? because you do have vertical asymptotes at 0 and pi for cotangent x. So those are actually extraneous solutions, guys. Those don't count. Because if you put it back into the original equation, you divide by 0. That's a problem. So we don't include it. Those are extraneous solutions. All right. Let me just kind of quickly tell you how to approach these problems, and then I'm gonna have Alex take over. Here, what you want to do is move the tan x over, factor out the tan x. I trust you could do what I trust you know what to do afterwards. Likewise here, move everything to one side, and think of it as like a quadratic equation that you can factor. I think 2a so then a equals 1/2. So cosine x equals 1/2. Or a equals -2. Can that happen? Cosine equal -2? No, that can't happen. So actually, and then you can solve for the rest after that. And I think there's still going to be the restricted domain. Well, it says find all solutions, so actually you should do a general solution in that case, but that's okay. I know you guys can handle that. So anyway, I'll stop there. You guys should be able to handle your homework. Alex, did you want to have them get out devices?
Yeah.
Okay, do you want to connect or?
Yeah, I think that's a good
Okay,
idea.
let's get out. You got. Let me disconnect. All right. Okay, so this is Alex, one of my former students. He's working on an app. He's gonna share with you guys. So, all right, let me disconnect. Oh, I need a.
Oh, I was gonna just use yours.
Oh, then yeah. Shoot.
Yeah. I'll just use like the browser and
Okay.
no big deal.
Hold on. Let me stop recording.